This is a typical slope problem. We have an object here that has a mass of 120 grams. We're putting it on a slope of 19 degrees to the horizontal. It has a coefficient of friction on the surface here of 0.17, and when we put it on the slope, it accelerates down the slope. What is that acceleration? Here's a diagram of the situation. We have the slope here, the object on the slope. The view is a cross-section with up, down in this direction, left, right in this direction. And I've shown the three forces that are acting on the object on the slope. As usual, there's gravity downwards. There's a frictional force along the slope, and it's opposing the motion, so it will be pointing up the slope. And then there'll be the normal force, which is always perpendicular to the surface itself. Now, the trick to solving a slope problem is to change our frame of reference, change our coordinates, so that we are lined up with the slope itself. So instead of using this one, we're going to be using a new coordinate system which is perpendicular to the slope and along the slope. So generally we don't have good names for those. I tend to call them y for the perpendicular and x for along the slope. This makes the problem a little bit simpler because now the normal force is purely in the y direction, the frictional force is in the negative x direction, but gravity is now at a weird angle compared to our coordinates. So we're going to decompose the gravity force into two components. So we're going to have a component that is perpendicular to the slope, like that. So we'll call that FGY, and there'll be a component parallel to the slope, like that, and we'll call this FGX. Now, the other part of the trick to this problem is to recognize that this angle here that the slope makes with the horizontal is exactly the same angle as the angle here. So this angle here will also be 19 degrees because the normal to the surface has been tilted by the same amount with respect to vertical as the slope has been tilted with respect to horizontal. And that means that the normal is still perpendicular to the surface. Now we write down the given information for the problem. We have the mass of 120 grams, which we will transform into 0.12 kilograms, the coefficient of friction 0.17, the angle of 19 degrees, and we will need G equals 9.8 meters per second squared because the force that is actually causing the object to accelerate is a component of gravity. What we're required to find in this particular problem is the acceleration. We don't know the value yet, but we know the units will be meters per second squared. For the analysis part of this problem, we need to analyze the forces that are acting on the object and try and figure out how that's going to cause it to accelerate. So, the net force is a combination of these three forces, but now we have gravity divided up into the x and y components. We can look at the net force in the two directions here, the x and y direction. In the y direction, the normal force is positive y, the FGY component is in the negative direction, and those two will add up to 0 because there's no acceleration in the y direction. The object stays on the slopes with a constant y value. So we know that Fn is going to be equal to Fgy. In the x direction, we do expect an acceleration, so the two forces that are acting along the slope itself in the x direction are the friction acting in the negative x direction and the x component of gravity, Fgx, going in the positive x direction. So those will not add up to 0, that will add up to the net force. So the net force on the object will be in the x direction, and it will be equal to Fgx minus the force of friction. So those are the two parts of the forces that are acting on the object. And we'll need both of these formulas in order to solve the problem completely. Now, when we're trying to find the components of the gravity, they are going to be, again, in the diagram here. The y component of gravity is adjacent to the 19-degree angle, so it will be the hypotenuse times the cosine of the angle. So this will be equal to Fg, which is the hypotenuse, times the cosine of theta. And Fgx, which will be opposite the angle here, will be the hypotenuse times the sine of the angle. So we can replace Fgx with Fg sine theta. Now we can do a couple more steps here. Fg, as always, on the surface of the Earth is going to be equal to mg. So the normal force being equal to the y component of gravity will be equal to mg cos theta. And similarly here, this will be mg sine theta. But what about the force of friction? Well, we have another formula for friction. The force of friction is equal to mu times the normal force. So we're going to substitute that into this formula here, mu times the normal force, and then we've just found out what the normal force is equal to, so that will be mu mg cos theta. So there's our formula for the net force acting, and by Newton's second law, all of that will be equal to ma. Newton's second law being F net equals ma. So now we have a combined formula. We're still trying to solve for the a, but that makes it really easy in this problem because we've got m, m, m. And we can divide both sides of the equation by m, both parts of the binomial here. So all of the m's cancel out. It really doesn't matter what mass the object has. And that leaves us with our final formula that the acceleration will be equal to g sine theta minus mu g cos theta. Now that we have a formula for our required piece of information in terms of the given information, we're going to rewrite that using the numbers and symbols that we were given in the problem. Getting out the calculator, we can now put the numbers in and calculate the answer. The combination of g sine theta is the x component of gravity, and it comes out to be 3.19 approximately meters per second squared. and that's how fast the object would accelerate if there was no friction. The friction will reduce the acceleration by the coefficient of friction times the normal force, or the y component of gravity, and so that reduces it by about 1.58 meters per second squared. Putting the two parts together, we get the net acceleration of about 1.6 meters per second squared. So now we can write the final answer to the question. The object will accelerate at 1.6 meters per second squared. We're rounding off to two significant figures because our given information was all to two significant figures.